So for my final lecture, I want to talk about neutrinos and supernova, and I have a guest lecturer. You'll see that I stole a lot of slides from him, of Georg Ruffelt. He's in Munich. He does, I think he's still in Munich. Does a lot of neutrino work with the Max Planck for astrophysics group in Munich as one of the neutrino experts. As I was preparing for this, he came and gave a very nice overview of neutrinos, so I decided I would use a portion of his slides, and you'll see them when they're his slides because he has a little label underneath for all his slides with his name on it. So those are the things that are almost certainly right. The rest of the stuff is mine. You can trust it as you may. So neutrinos are at the kind of basis for core collapse supernova. They're what produce. We believe the energy coming out of the protoneutron star is transmitted through neutrinos and then deposited and drives our explosion, or helps drive our explosion. So they're key for neutrino for the supernova engine. It turns out that we actually knew that neutrinos came out of stellar collapse back in 1941. So remember, we didn't really even propose a collapse down to a neutron star until 1934, I guess there was at least one paper by Bade and Zucchi, and then by 1938 they were pushing it very strongly. By 1941, George Gamow said that, there it is right there, said that the high temperatures that you're going to get when you collapse down to a neutron star are going to emit a lot of neutrinos. So we've known neutrinos would be in a core collapse supernova from the beginning. What the neutrino scientists will always tell you, the neutrino physicists will point out, is that when you collapse down to a neutron star, a protoneutron star, most of the energy is converted into neutrinos. Most of the energy emitted comes in neutrinos. So 99% of the energy in a core collapse comes out in neutrinos. Another 1% comes out in the explosion energy itself, and only about 0.01% comes out in photons. So Sanjay Reddy often cites these numbers and points out that that's, why are you worrying about this 0.01% when 99% of the energy is coming out in neutrinos? Of course, the reason why we worry about the 0.01% is we see a lot of supernova light curves. We do not see that. We only have one supernova with neutrinos, despite the fact that the neutrino luminosity is 10 to the 19 times the light of the sun. There has been more effort looking for supernova in the diffuse neutrino background with the IceCube telescope. So the diffuse supernova neutrino background is comparable to the extragalactic background light. It's 10% of the cosmic radiation density. So it is a big role even in the in the galaxy, in the universe as a whole. So it's playing a big role there. There's a lot of physics you can get. Neutrinos are the best probe of that inner workings of the supernova, and we'll talk a little bit about what neutrinos can tell us, what we are doing with neutrinos, but before I do that, I want to talk a little bit about how we detect them. So here it is, supernova 1987A. These were the neutrinos detected. They were actually detected by 3 detectors, Kemi, the Irvine, Michigan, Brookhaven mission in the US, and there was a detection in Russia. The problem with this particular detection is it was off in timing with the 2 other detections, which there were models predicted to how you could get something off in timing. At this point in time, I think the bulk of scientists think that these were probably real results, and this was just finding some data, so it's not a high enough signal to be true. There's ways you can say there was some delay in the neutrinos getting to the boxon detector, but I think for the most part we focus on these neutrinos. There were 17 of them. There were more than 17 squared papers written on these 17 neutrinos, so they played a very pivotal role in understanding supernova. Here are the detectors that made these observations. So this is their IMB detector. They're essentially vats of water with photomultiplier tubes The neutrino enters, it interacts, it causes a particle to go faster than the speed of light in that water. It emits Cherenkov radiation, and you observe that Cherenkov radiation. So here's the IMB detector. Here is the Kemi detector, and this is actually the detection, the photomultiplier tubes that turned on for event number 9 from those neutrinos. So you can see the Cherenkov radiation sent enough light that quite a few photomultiplier tubes made detections, and that would be one event for a neutrino. So it's like cosmic ray detectors in that sense. Just to show you how hard these detections were and how lucky we got, this was the Kemi detector. They were having troubles with radon getting put into the, getting in the detector fluid, and they were having to filter it out. So they would have a recirculation that would filter out this radon. And here is this is in 1986 of July. This is the background noise from radon. So they're trying to deal with it, they're trying to fix it. Now it's November of 1986. Starting to get to January of 1987, they finally got something that's starting to work. This is January, mid-January of 1987. This is when the supernova went off. Had they been just a couple months slower in fixing this problem, they wouldn't have seen a detection. And then they had a problem at later times that caused more issues, and the noise went up again. And until they fixed it, now the noise is fairly low. But there's a huge period where they were bad and then bad again, and it just so happens that 1987A went off at the right time. So this is, I think there's lots of cases where scientists are unlucky. This is one where they were fairly lucky in getting the device running in just enough time. This is a slide from Nakahata. So there's a whole series of, with these detections, there's a whole series of next generation detectors being planned. There's IceCube generation 2. So IceCube is one of the detectors. It is in the South Pole. What they do is they use the ice of the South Pole as their fluid. That's what the neutrinos are going to interact with. Then they melt the ice and send strands of photomultiplier tubes down through that ice, and those photomultiplier tubes are then detecting the Cherenkov radiation from the neutrinos interacting with the ice. The advantage of this is the detector is fairly cheap to build because you don't have to build a big vat and put water in it. You can actually just sink photomultiplier tubes down in. It has some disadvantages. It's less sensitive to some of the lower energy neutrinos than some of the other detectors that are being made. So there's a class of, they're currently running, taking a lot of data. They're planning to expand extensively. So this will be a big detector in the reasonably near future. There's things like megaton class water Cherenkov detectors. The Hyper-K is the Hyper-Kamiokande is the classic example. This will get the kind of neutrino statistics that IceCube, the generation 2 IceCube will get. So these two classes of detectors are likely to detect a lot more neutrinos than what we have now. So if you had with these detectors running and we had a supernova like 1987A, instead of having 17 neutrinos, we'd have more like thousands. So that it would make a much stronger signal. There's scintillation detectors. They're sensitive to different aspects of the neutrino, different neutrino species. There's Juno in China. There's Reno 50 in Korea. There's the Boxon large volume scintillator detector being developed that should be, since they're sensitive to different species of neutrinos, they will provide extra information. There's also some liquid argon time projection chamber detectors being planned. It is, a lot of these things depend on how the funding is going, but right now it looks like across the world we have quite a few detectors being built. So there's, the US is still trying to figure out what it wants to do for neutrinos. But they have several proposals. Here's Super-K, where Hyper-K will be, Boxon, and some of the other. Diabays, there's ones that are similar to the IceCube, where instead of using the ice as the material where the neutrinos interact. They're using the ocean, and they've been studying detectors where they put photomultiplier tubes in the ocean and make an array there and use the ocean as the detector. There they have to actually be very careful of knowing how are the photomultiplier tubes moving with time, so they have they're doing a lot of efforts to improve those detections. The neutrinos are in a similar boat as gravitational waves in that the current and next generation neutrino detectors are sensitive out to about 100 kiloparsecs. The good news is if we do get a galactic supernova, the neutrino signal will be exquisite. It will be a lot of neutrino counts. We'll get spectra, we'll get time-dependent features. We'll be able to probe a lot of physics. But if we really want to get out to something like the Andromeda galaxy cluster, we're going to need a lot more, a bigger, something that's roughly 30 times super K. We're going to need something that's big enough that it's going to take real funding to get that. Once we get out there, neutrinos will be detected in a more regular way. And so I think neutrinos maybe even have a higher potential to detecting supernova than gravitational waves at this point. The optimism of neutrino scientists has often been because of, being optimistic about the rate of supernova in galaxies. Here's two examples. Here's M31. This galaxy, the last observed supernova in Andromeda was in 1885. And then you have NGC 6946, the fireworks galaxy, that has had, over the course of the last century, multiple supernovae. So you're looking at almost 10 supernova. So the supernova rate seems to be hard to determine just by looking at galaxies. Some are active, some are active, like the fireworks galaxy, some are not. And so this leads to a wide range of predictions for the rate of supernova, and hence tells you how often you should get a detection. So there's the statistics done by just looking at the supernova rate in a whole host of galaxies and then inferring what's the supernova rate in the Milky Way based on those host of galaxies. And those rates tend to be, the optimistic ones tend to say that the rate could be almost up to 3 per century in a Milky Way mass galaxy, down to about 1.5 per century. The less optimistic ones, the Capellaro and Tarato, and I'm a pessimist, so I always take the lowest numbers. It's less than 1 per century. So the Milky Way, we're still due for one because we haven't had one in the last century, but it is at the level of the rate could be as low as 0.8 per century. If you look at the gamma rays from aluminum-26, you assume supernova produce a certain amount of aluminum-26, and then you look for the gamma rays of aluminum-26. This is Roland Deal. You get a rate that's fairly similar to the rate predicted from just observing a wide set of supernova. If you try to go and do the low number statistics on looking at historical galactic supernova, so historical supernova in the Milky Way, you get rates that are much higher. And this is what had the supernova neutrino folk more optimistic, because they were getting up to about 5 to 7 a century. So they were thinking, we're going to get one every about 15 years. And so we're really, at that point, we were really due for this. I think this is mostly low number statistics, and clearly it's not happening now. As time goes on, these rates are starting to go down. These rates are staying these rates won't change because they're on large number statistics. There are upper limit constraints you can place based on not seeing any galactic neutrino burst, and so that number keeps on going down with time. So these are the kind of estimates people make. If you're optimistic, you take these numbers and you say every 15 years we should get a burst. If you're pessimistic, you say, well, it's once every 100 years, so I really have to get lucky if it's going to happen in my lifetime. And depending on who you are, you take either of these. I think what's really going to make the difference is as we get to these big detectors, we'll start going beyond two nearby clusters and up the rate a lot, and get beyond the 100 kiloparsec range. Nonetheless, oops, wrong direction. The supernova community has, the supernova neutrino community has already developed and prepared themselves for what will happen when they detect a neutrino. They have made a system called SNOOS, that is the supernova early warning system. The advantage of neutrinos is they're the first thing you'll see. They happen before, they happen in the core, they get emitted. You have to wait till the shock gets to the outside of the star to see any photon light. So they would be the first signal for a supernova going off. They have already designed a plan where they immediately upon learning this, they send in information to the astronomy optical observatories, and those observatories can then observe these supernova. So they're prepared, they're ready with the idea that they just might get lucky. They have to, they have to be worried. So this is a thing that's been running for over 10 years, and it'll run hopefully for the next few hundred years. So why are neutrinos useful? Neutrinos actually are good probes, and we'll talk about features of a lot of these. You can use them by looking at the neutrinos. You can study neutrino masses and mixings. So we already did this with 1987A. We knew things like the mass of the neutrino from the difference in time the neutrinos took to get to us as the photons are. So we had a prediction from when the supernova went off. The neutrinos came essentially during that time. That puts an upper limit on the mass of the neutrino. So we could place limits on the mass of the neutrino. They were going essentially near the speed of light. Those papers were out right after 1987A went off. People immediately realized that role and they can play on it. You can also look at, and we're going to talk a lot more about this, if you can get a neutrino spectrum, you can study things like collective flavor conversion in neutrinos. So we'll talk in a lot more detail about this because it's one of the new exciting results coming out of neutrino physics for supernova. We already discussed this, neutrinos, as far as how they play a role in core collapse physics, and we'll go through some of these examples. They're an early warning for the supernova going off. So we'll get a warning that a supernova is going off. We'll put our optical telescopes there, and we're likely then to get the shock breakout of the supernova. We only have a few shock breakout supernova likers at the moment. They're all serendipitous, but we could get one where we actually know the supernova is going off, get enough location from the neutrinos to point our telescopes. We study the prompt neutrino burst coming out, helps us study the equation of state. If you see any fast time variations, you can look at hydro instabilities. We'll talk about both of these more. There's a big thing of, oh, well, we have neutrinos and they're multi-messenger along with gravitational waves. There has been a big thing, especially with the detection of gravitational waves, where the gravitational wave community keeps on saying, oh, now we're doing multi-messenger astronomy. Well, we've been doing it forever with neutrinos, and for me, multi-messenger is gamma rays, nucleosynthesis, optical photons. They're different messengers. So it's not a new thing. Multi-messenger is not a new test, and neutrinos and gravitational waves are not the only new messengers. But this is a Geyer-Grafelt slide, and the neutrino physicists and the gravitational wave physicists all think that they're the only owners of multi-messenger. Multi-messenger is saying we're going to take all the data. All the things we've discussed all week have been multi-messenger constraints. Remnant masses are another multi-messenger constraint. Even if you get black hole formation, you still get neutrinos. And I'm not going to talk about this in more detail, but that collapse for black hole formation, the first collapse is down to a protoneutron star. Only in these very massive stars do you collapse to a black hole without making a neutron star. And even in that case, it forms a proto-black hole, and you'll get neutrinos during that collapse. So in some cases, if you don't get any explosion whatsoever, the neutrino burst might be the only thing you see. And then there's the diffuse supernova neutrino background studies that people do. Finally, there's also, you can use neutrinos to probe some of the other particle physics effects like axions, non-standard neutrino physics, and time of flight tests. So there is some other particle physics that can be studied and non-standard physics that can be studied with neutrinos. So they're actually very rich. These are, when we get a galactic supernova, that's going to change our entire picture, and it's mostly because of the neutrino signal. So here it is. We'll go through some of the examples. First is bounce. This is that bounce signal. When you get that collapse and bounce, you get a burst of neutrinos. So this is, I think we can even look at this light curve and see that effect. So this is some results by Barras et al. In 2003. The star collapses. It's collapsing. The neutrino signal is going up. When it reaches a certain high density, the neutrinos start to get trapped, and the neutrino flux starts going down. Then it bounces, and that shock moves out. That protoneutron star shock is moving out. When the protoneutron star shock moves out to the place where the neutrinos are no longer trapped, you get this large neutrino signal. So this is characteristic. All explosions have this little feature where they go up, neutrinos are trapped, go down, and then the bounce happens and they emit neutrinos. You can look at these. Here's the signal in the Serrant et al. Result. This was working with Willy Benz. He had the neutrinos going up, goes down, and then goes up again, and that's his neutrino flux. These are on slightly different scales. So this is linear in the flux. This is log in the flux. So that's the primary difference you're seeing here. So then you have neutrino species. You can also get the neutrino energies. We are predicting more and more spectra with these bounces, and I'll show a slide in a bit where I show how the equation of state affects this. But this is the characteristic neutrino signal that we look at. Remember, we have this convective engine. So again, let's go back. After it bounces and stalls, there's where the shock stalled. Now it gets convective. There are ways to probe. The neutrinos can actually probe this convection by looking at the neutrino signal. If you get a here's just a normal. If I take something like the plot before, this is what the neutrinos luminosities look like. They actually have these features. This is from that convection. Some kind of random features from the convection. If you have an upwelling where you change the optical depth for the neutrinos just slightly, that's enough to change the neutrino flux. Where you really will see a strong signal for neutrino features is if there is a really low mode convection where it's just sloshing back and forth. So this is a simulation by Tombola et al. And the convection is sloshing back and forth, and as it sloshes back and forth, the neutrino flux varies in a kind of easily defined way, because it's just the sloshing time of that convection. So really low mode convection will have a pretty decided signature. With 17 neutrinos, you couldn't see any of this, but when you start to get a galactic supernova with the current detectors, where you're getting thousands of neutrinos, you start to be able to probe this kind of physics. After that phase, you have the launch of the explosion, then you have material move out, and then it falls back on, and you get another set of neutrino flux. This neutrino flux is important for neutron star cooling, so this is just time after the explosion accretion rate. Here's some of these fallback rates. The fallback rate can be up to 1 solar mass per second. So it's a huge fallback rate. We already discussed how that drives outflows and can produce our process, but it also can produce strong neutrino luminosities of 10 to the 51 ergs per second. So you can get 10 to the 50, 10 to the 51 ergs per second for fallback for maybe up to 10 seconds after the explosion slowly going down as the accretion rate falls off. Beyond 10 seconds, there is still neutrino emission. And here's some Burroughs 1988 calculations of the cooling of a neutron star after it forms. Most of the energy in the early, the first 20,000 seconds or so is coming out in neutrinos. So neutrinos drive the cooling for neutron stars at early times, and these are things that you can measure. The other things that people have done, and I don't have a slide on this, is they look at the evolution of neutron stars, and they look at that cooling, and they can study some of the equation of state features based on the temperatures of different young neutron stars. So there's a lot of studies looking at neutrino cooling for neutron stars as well. The equation of state is one of the big constraints that we have on, that we want to probe when we study supernova. It can play a big role in the supernova explosion. Neutrinos are a way to probe what that equation of state does. So the equation of state can affect how the bounce occurs. It can then affect that, by affecting the bounce, it can change the convection in the core. And it also plays a big role on the neutrino emission and the opacities for neutrinos. And the issue here is the outer side, so a neutron star, this is a cold neutron star, but there are similar features in the neutron star in a core collapse supernova that's a little bit hotter. You still have something that's like a crust. You have an atmosphere and an ocean on top. The atmosphere and the ocean are at conditions of, well, okay, so supernova, really we start carrying at about 10 to the 10 grams per centimeter cubed, where there's heavy elements there. There's a lot of heavy elements just in this nuclear statistical equilibrium conditions that we're in. You get heavier and heavier elements, and then you get this crust region where you're starting to get denser and denser material, and eventually you hit this pasta phase of the equation of state, where there's clumps of large ion clumps. I don't know how to describe them better than that, where there's a lattice of the materials. You get a place first where you're just forming clumps, then they form sheets, well, they form rods, then sheets, and then they start forming, most of everything is a solid. You get to the superfluid stage after that, as you get beyond this. This is the kind of region that the neutrinos can help actually probe. So you can actually start studying some of these weird features of the equation of state with neutrinos. Right now, most of the equation of states that have been produced are not hot. They produce equations of state that assume zero temperature. Well, the problem with the supernova is you cannot make those assumptions, so we don't have that many equations of state that we can use. There's a growing list, but Sumiyoshi did do a comparison between one of the Shen's equation of state. There's actually two Shens, one from Japan, one from China, making equations of state for supernova. And there's only really one other big group making equations of state for supernova, and that's Jim Latimer and his team working with Doug Swesty. So there's these kind of three equations of state. They used one of the Shen equations of state and the Jim Latimer one. We're hoping that more equations of state for hot material are going to come out soon. Sumiyoshi did a comparison. Here's how those neutrinos are affected. This is the neutrino luminosity versus time, and you see quite a different neutrino luminosity. Sadly, he plotted in a linear form, so this peak dominates, but here's the kind of differences you get in the neutrino luminosity. Here's for the electron neutrinos, this is for the electron antineutrinos. You're looking at 10-20% differences in the neutrino fluxes caused by these assumptions. Kago says Tomas Borosyanka, American Romp, also studied this. They played with different masses. They played with different forms of neutrino transport. So the problem with the neutrino effects is neutrino transport can be as big an effect as the nuclear equation of state. But here again, you see, here's neutrino luminosity as a function of time. This is the anti-electron neutrino luminosity. This is the mu and tau neutrino luminosity as a function of time. So electron neutrinos, anti-electron neutrinos, and the mu and tau neutrino fluxes as a function of time. And here they use also the Wolf equation of state, which was a simplified equation of state when they were doing the effects. But you see that they all produce slightly different results. Here you see them in the bounce itself, so they're seeing differences in the bounce itself. I think there's a lot more work to be done by us theorists to figure out exactly what is the signature from these neutrinos and how can we learn something from them. And that's one of the focus points that the theorists are working on to prepare for this galactic supernova event. And one of the big features there is studying the transport. So I want to go over transport again because we talk about, you guys are getting this a lot. Transport of something is important in supernova all across the board. It's transport of photons when we're looking at the light curves. It's transport of neutrinos when we're looking in the engine. It turns out it's the same equation. So you solve it with the same different approximations. You can again use diffusion. You can take a first moment over angle and get diffusion. Second moment, get variable Eddington factors. You can average over energy group, do gray. So a lot of the early calculations, in fact, a lot of the calculations that we have are either gray flux limited diffusion or multi-group flux limited diffusion, where you have a set of groups doing the neutrino transport. You could remove the time-dependent term. I don't know of any group that does that in the neutrino area. You can ignore spatial terms. So for the longest time, the Max Planck for Astrophysics group led by Thomas Janka did a thing where they did instead of doing full neutrino transport, they did a series of 1D neutrino transport along different angles. What you're missing there is any neutrino transport across those 1D layers. And we'll see an example where this could be an important factor if you do it wrong. So you have the same kind of transport methods that we discussed before. Let's look at a problem like this one, where I had a rotating star. I have now this dense disk. I have neutrinos coming out, but I have this dense disk around that protoneutron star that's coming up toward that protoneutron star. The convective region is right down there. This material is much more dense than this material. And I'm going to ask the question, what happens if I use different transport schemes for this kind of physics? So here's my disk. Here's my hot protoneutron star. It's emitting neutrinos. And this was done by Kent Budge in Los Alamos National Laboratory. He's a transport expert, so he studies just transport. I convinced him to do some neutrino physics. So here's the calculation doing flux limit diffusion. He has put this this is a toy model, he has put this block here from that disk and asked, how does the neutrino flow out? So if you were doing just a simple 1D, along different rays, you just get going out straight this direction. You wouldn't get any of this curvature that flux limited diffusion does. This is what flux limited diffusion does. Because it's assuming the neutrinos have an angular distribution, it kind of flows in all directions. So it's almost like an isotropic diffusion, and it flows around that box. That's clearly not right. In fact, here's what the right answer looks like. We go to the Monte Carlo. This Monte Carlo is, again, our gold standard if we can have enough packets. And in this case, he could put a lot of packets. This is what the transport should look like. So it has material coming out, and then it has some some material flowing around this direction. But most of the neutrinos would be coming out in one direction. So this was again, the advantages of Monte Carlo is you can do the answer fairly accurately if you can have enough packets. The problems with it is it's really expensive if you need to get the number of packets you need to do these calculations. And then there's these discretize the angle methods, these PN or SN, where you've chosen some kind of quadrature weights or spherical harmonics to weight the angular distribution, and then you do a calculation. And this is probably, again, I didn't write it down. It's either an S4 or an S6 calculation. It's probably an S6. So this is an S6 calculation of that neutrino transport where they've used 6 basis vectors, 6 quadrature weights to represent the radiation. And you can see that this is one of the issues with using one of these discretized methods to doing neutrino transport. And so you're definitely going to have stability issues if you do this kind of neutrino transport. These are the methods we have, the numerical tools that we can use. We do the best we can with them. I would say for the most part, most of their results are produced with multi-group flux limited diffusion, aside from this group in Germany that does these series of better transport but along rays, so this ray transport that they're using. Both have advantages and disadvantages. Until we get this solved, some of the using neutrinos as a probe of some of this nuclear physics is going to have to wait because we really have to get that transport done correctly. One of the coolest features of neutrinos is they can probe weird, new neutrino physics. And one of the big things with neutrinos that we've focused on a lot, especially the group by George Fuller, is the possibility of neutrino oscillations. So the kind of classic neutrino oscillation features that everyone knows is the MSW neutrino oscillations. People have studied this in detail, looking at how can it affect the nucleosynthesis in supernova, how can it affect the energetics in supernova. There are kind of 3 different regimes for neutrino oscillations. There's the standard MSW or vacuum neutrino oscillation area where the density is fairly low. Then you get neutrinos oscillating, but they're oscillating in a almost solitary way. So they're oscillating, but they don't have to interact with other neutrinos. They're interacting with matter. These kind of matter interactions can happen out well beyond the neutrino sphere in the kind of explosion as you're moving out the explosion. This will change the neutrino signal for things like if you're making weird elements like lanthanide or tantalum through neutrino spallation effects. So that oscillation effect was the first one that people studied. There are technically neutrino-enhanced MSW effects in the protoneutron star itself, and probably the issue with those neutrino oscillations is you can oscillate, but then we're thermalizing the neutrinos anyway deep in the core, so it doesn't really change the neutrino spectrum that much unless you can oscillate into sterile neutrinos. And I think I have some slides on sterile neutrinos that we can talk about. In fact, the next slide will be a sterile neutrino slide. So here you can get sterile neutrino oscillations. And the new kind of idea is this collective oscillation regime where it's just outside of the neutrino sphere, and the oscillation is neutrinos with neutrinos. And that kind of collective neutrino oscillations may play a big role in the supernova engine. Definitely it could play a role in the nucleosynthesis and also in the neutrino spectrum. And we can use then the neutrino spectrum to learn about neutrino oscillations. So first I wanted to talk about the sterile neutrino oscillations. The idea here by Fuller and his collaborators, it's Alex Kusenko and George Fuller, was to look at neutrinos oscillating to sterile neutrinos in the core of the protoneutron star. We know that we know oscillations happen. If sterile neutrinos exist, we expect them to oscillate into sterile neutrinos. So we expect oscillations to sterile neutrinos. If you talk to the neutrino scientist, I went to a meeting, one of these KITP 6-month workshops, spent 3 months there, where all the neutrino experts were convinced that sterile neutrinos do exist. So most of them believe in sterile neutrinos. If you have oscillations into sterile neutrinos, you can get an interaction where you have a mu and a anti-mu neutrino and mu neutrino making an anti-mu neutrino and a sterile neutrino. And unfortunately, they can get a wide variety of numbers of how often these processes happen. But they can make these neutrino oscillations. There's also tau plus anti-tau plus tau, tau plus mu, anti-tau plus mu. So you can get a range of neutrino interactions. They have different amplitudes. They make different fluxes. And the neutrino luminosity in these sterile neutrinos can get as high as 10 to the 49 ergs per second per MeV. So in the end, this is 10 to the 51 ergs of neutrino emission per second. So it's you can get up to a very high neutrino flux dominating what is coming out of the supernova. If this actually happens, you can alter the flux of neutrinos coming out. If the sterile neutrinos can then decay to something like to gamma rays, they can deposit energy and produce the explosion. The neutrinos carry away with momentum. If it's in a highly magnetized neutron star, you can actually get asymmetric neutrino emission and produce kicks. So it's been used for to explain a lot of features. The problem is the uncertainties are either you can get most of the energy emitted in sterile neutrinos, or you can get essentially no neutrino energy emitted in neutrinos. So that's the error bars on these kinds of calculations. So that's sterile neutrinos. The other neutrino emission you can get is through these collective oscillations. And here, to calculate collective oscillations, where it's neutrino-neutrino oscillations, you need to know how are unfortunately, the cross-section for this is angle dependent. So now you need to know the full neutrino angular distribution. This requires then that higher order neutrino transport, either Monte Carlo neutrinos or these SN or PN models, these discretized models for the angles. We need to do that in our time-dependent codes to actually learn this physics. People have been probing how important this physics is. Duran et al. In 2009 did a series of papers on this where they instead just took a flat material space and said, I'm not going to actually calculate the time-dependent neutrino oscillation. I'm going to say, in this exact condition, I'm going to then run it as a steady state and ask the question, what happens to the neutrino oscillations? And so he had to look at all the angles, make sure he was calculating all the angles accurately, and then he did a calculation. And here's a result. Let's see if I can get this movie to run. So this is a result of the, oops, it's not running. Let's get it back to the beginning. So here's the beginning. It starts to, it's moving as the neutrino spectrum is, why did it jump? Let's see if I can get this. Pause. I'll just move it out all the way to the end and then try to start it over. But you can see as it moves out, this is the mu neutrino spectrum, this is the electron neutrino spectrum initially, and this is the neutrino spectrum as it changes, as those neutrino features go out from near on the protoneutron star surface out to 250 kilometers. So at this point, this is the neutrino spectrum at about 180 kilometers from the surface. So the neutrino spectrum oscillates. These plots here are the angle distribution of the neutrinos versus the energy of the neutrinos. In the end, what we get out is just the energy of the neutrinos, and so you see at late times it starts to evolve into this weird feature that is very different than what you would expect from just no oscillation case. There are lots of studies on how the neutrino flux can vary. They have a lot of models, so this is just one model for the neutrino oscillation. There are some models where the effect is much less, so you don't see it as easily. There are models where the effect is, well, there's actually, this is probably one of the dominant models where, for whatever reason, it doesn't want to start at the very, it's there. Yeah, now it's going from the very beginning. But you can see it starts off, the neutrino flux starts off here. As it moves through the star, it slowly changes its spectrum until it gets to a point that had that final feature in the neutrino flux. So these are new physics studied the last decade, studied for supernova neutrinos. If this actually happens and we get a neutrino signal, it doesn't matter about any of the uncertainties in our physics. The mu and tau neutrino spectrum is always very different than the electron neutrino spectrum. If the electron neutrinos coming out of the supernova look more like the mu and tau spectrum, we know that this kind of oscillation physics is occurring, and that's a nice feature. So that's where we can really use neutrinos to probe this nuclear physics with supernova, and I think this is one of the exciting things that the first thing we'll do when we get a galactic supernova is see with the spectrum, do these kind of features really exist? But what do we do while we're waiting? We don't have a galactic supernova happening. How can we really probe this supernova physics? The kind of one other way we can probe it is by saying, how do these neutrinos affect the rest of the supernova? So we know it can change the energy. If we can make strong constraints, we change that energy and then we try somehow tie it to light curves. So I just gave an example of light curves. So one way to do it is to take it and say, what are the predictions for this neutrino oscillation or this different neutrino physics on the explosion mechanism? This tends to be harder to do because it's usually unclear how effective the neutrinos are on the explosion mechanism, but we already make some constraints. So we can look at things and say, okay, the conversion to sterile neutrinos, we can do that. It cannot be that the sterile neutrinos are all the energy is converted to sterile neutrinos and then the sterile neutrinos don't decay. If that happened, we wouldn't get explosions at all. It also can't be that the sterile neutrinos most of the energy is converted to stellar neutrinos. It gets out to beyond the neutrino sphere, and these all decay within the star. because that would make an explosion of 10 to the 53 erg. So we know that only about 1% of the energy can decay. We've done a lot of tests like this of things like axion physics, where we say, okay, there's something called a dark photon. It's a form of dark energy. You can have it. You produce this dark photon. Only we can place limits on how much energy is produced by these dark photons in supernova. It actually is a stronger constraint on dark photons than cosmology is on this kind of dark energy and dark matter possibilities. So we are ruling out some things on this physics, only because the physics is extremely uncertain with this kind of explosion energy. The alternate way to do it, and I think where neutrinos have a stronger chance and more power in actually trying to constrain the explosion, is where you look at the nucleosynthetic yields. And the reason is the neutrinos really determine the electron fraction in the ejecta. And depending on how they reset the ejecta electron fraction, it will change the yield. So things like the titanium to nickel ratios that we see in CAS A, we can study and say, this is what the electron fraction of the ejected material has to be. And then we can go back to the neutrino physicists and say, look, what do we need from you? What kind of spectra do we need in the neutrinos to set that electron fraction? And if the spectrum is much different than that, we can start to place constraints on that neutrino physics. So there are attempts to do this while we're waiting for a neutrino detection, to use these kind of indirect observations to constrain this neutrino physics. And what we do is we actually take in these models for things like neutrino oscillations and put them into the rest of our calculations to get nucleosynthetic yields. Neutrino oscillations have been used for a long time to explain our process. George Fuller has a number of students that did this for their thesis. Yang Chen was probably one of the first, but Gail McLaughlin and then her student Rebecca Sermon studied this in detail. So there's a lot of science going on to how does it affect things like our process as well. And with that, I want to finish what I was covering on neutrinos and give a little summary of what the series of lectures we went through kind of covered. So I think neutrinos are one of the strongest probes, the best probe of that inner engine that we have. They come directly from there. They will help us study the equation of state. They will help us study aspects of the explosion, the convection, asymmetries. We will be able to study that with neutrinos, and they help us study neutrino physics itself. So we'll actually use neutrino detections to probe this physics. Gravitational waves also probe that inner working. They focus more on that rotation. Gravitational waves will tell us how fast our core is rotating if we get a signal. So if we have a galactic supernova, we're going to know fairly well what a lot of the neutrino physics that are uncertainties in our models now will get really pinned down. We'll understand neutrino oscillations a lot better than we do now. They will be probably the biggest constraint of neutrino oscillations that man can produce at this point, but we have to wait for a galactic detection. So they're great, just like gravitational waves, but they really need a galactic detection to do studies. And it'll be nice alternative probes to the picture we're getting from these less direct probes, things like the nucleosynthetic yields, the light curves. These will have a more direct probe of that inner working of the supernova. Let's go through what we actually had in this series of lectures. So we have a basic core collapse engine. It seems to match a lot of the features. We've used it to match the neutrinos. So this engine came about, it started, first proposed, core collapse was proposed in the 30s. In the 60s, we started to get an idea of how the collapse bounced. We started doing our first simulations. At this point, we're in the level of we're adding physics, we're improving the physics in our models, we're comparing now to a larger range of diagnostics. And this basic model seems to be doing well. When we get really detailed diagnostics, it is matching the data fairly well. It's gotten to the point that there are actually no other proposed models that are out there that match the data as well for normal supernova. But one of the constraints of this is this engine cannot explain the very energetic supernova, the hypernova that we see. The only way they're going to explain the superluminous supernova is if there are different processes to how the superluminous emission comes about. So remember, the photons that are coming out are just 0.01% of the energy. You have 1% of the energy in kinetic energy. If I can just change how I get that kinetic energy, I might be able to explain a superluminous supernova. However, I cannot get these hypernova that are 10 to the 52 ergs of kinetic energy. That we cannot explain with this engine. So it can't explain all of them, but it explains a lot of the observations that we see, things like the neutrinos, the energetics, the asymmetries. So the energetic constraint is not just getting that, but somehow releasing 10 to the 53 ergs time and time again, and mostly producing 10 to the 51 erg explosions. Especially with gamma ray bursts and hypernova, we need alternate engines. Alternate engines exist. Things like magnetars, collapsars, which are accretion disks around black holes, possibly accretion disks around neutron stars where you can produce strong magnetic fields. All this depends a lot on what is the angular momentum of the progenitor star, which we had discussions of yesterday afternoon. They also depend on what kind of magnetic fields are you producing in those progenitor stars before they collapse. So there's a lot of uncertainties in these models. We still do not model magnetic fields in the best. Magnetic fields are difficult to model in general. I don't know of too many codes that can actually model magnetic fields, first principles and match laboratory experiments that we have on the Earth. We struggle with using magnetic fields to match even the solar magnetic field evolution. There's lots of approximations when you do magnetic fields. So these models are a lot more uncertain than what I think the standard mechanism is. I do not think they will explain normal supernova, but I think they have a good chance of explaining a lot of the more exotic supernova that we're seeing that are core collapse. Things like GRBs, seems like hypernova. I think the data that really has pushed this engine to in the forefront, our standard engine in the forefront, has been this titanium observation. These clumps of titanium, this is not explained by a jet-like explosion. This titanium was made near the engine. This has to be telling us something about that convective motion. And there are lots of groups studying how can we probe this, how can we use these observations to really give us a handle on the supernova engine. I think that's one of the big constraints we have right now for our supernova engine, and it's really the final nail in the coffin for the jet-like explosions. They're not explaining at least Cas A. Now, it could be that there's a whole subclass, 20% of supernova are jet-like, but certainly the supernova that we have the best data on are not these jet-like explosions. Supernova light curves, I think this is where most of our data is. This is if we can get realistic and good models and beat down the uncertainties in the light curve models, they will be a great constraint on the engines. But there's still a lot of work to understanding this physics well enough that we can use these to constrain what the engine is actually doing. Where do we go from here? Well, there's a lot of work that can be done on to produce quantitative models. Progenitors, we had a lot of discussion on that yesterday. There's clearly lots of work to be done there. There's the model, but the good news is they're gradually getting better. So same with the supernova engine, we're gradually getting better. We're improving the equation of state and the neutrino physics with time. How we do the neutrino transport, we are improving. We're increasing the resolution so we do better on the turbulence modeling that we're studying. More groups are adding magnetic fields. Even if magnetic fields are not driving the explosion, they can still be important to the nature of the explosion. There's also lots of work that you could be doing on diagnostics. We could look at more detailed neutrino calculations where we include these neutrino oscillations in our light curve model, in our explosion models, to get really detailed neutrino spectra coming out of supernova. There's more work being spent on gravitational wave signals, looking at how, if this turbulence model is correct, what really does it predict for gravitational waves? Light curves, that's the one where we have a lot of physics. I think there's lots of uncertainties, but that's where we have lots of observations. So I think there should be, there's going to be a lot more work on doing these light curves. It's a hard calculation. Opacities are not easy. Implementing opacities are hard. It's not as simple as just saying, oh, I'm going to use Sobolev and be done with it. There's a lot of work that has to be done there. And in nucleosynthesis, I think we are starting to beat down the uncertainties there. You can combine working with people that measure these nucleosynthetic rates and do sensitivity studies, and there's a lot of work being done there. And with that, I will end my lectures, and this is the last one. Thanks. Thanks for your time.
So I was wondering, you showed statistics of the fireworks galaxy with the number of supernovae.
Yeah.
And you mentioned there in the text that one of them is a failed supernova.
It's a possible failed supernova, I should say that.
So does it mean that this is a massive star that is directly collapsing into a black hole?
So there's
Just fill in the second part of the question is that you later mentioned in the collapse phase of massive stars, where you might skip the proto-neutron star, phasing where it's going to approach a black hole, because you would have the neutrino emission. So what are we expecting?
So even, I think in this case, the star was not a 300 solar mass star, it was more modest. The observational group on this, it's, I'm not going to have all their names. Kachanik is one of them, where Chris Kachanik, where they just are looking at the galaxy, looking at all the bright stars, waiting for one of them to disappear. And the problem with this particular search is, and so this is really just a potential candidate, the problem with this particular observation is it could disappear because it really has died. It could disappear because a dust cloud got between you and the observation. So they don't know that this is it, but it's their best candidate, failed supernova. So it disappeared. And so you had a star there, it disappeared. In this case, it would have probably gone down to a proto-neutron star first, emitted a lot of neutrinos, but the convection wasn't enough to drive an explosion, so it just went down to a black hole. So it would have a nice neutrino signal had we had a detector good enough to see this far out and see these neutrinos. There is depending on, the rate of these is probably more like 10% the supernova rate. So in that sense, they're not going to contribute hugely to the diffuse supernova neutrino background. They're going to be 10% of it. They have some interesting features because the spectra evolves differently for a failed supernova than it does for a normal supernova, and you can actually study that failure. But it should have produced a nice, bright, bounce neutrino signal when it occurred. But it could also have just been a star that got covered by a dust cloud, and we don't see it right now. So if it reappears in a decade, then we know it was a dust cloud. If it never reappears, we still don't know. We just know that it's still not uncovered yet, or it has indeed failed and produced a black hole. The more they get of these kind of systems, the more people are going to believe they're seeing failed supernova, and that would be an exciting observation.
Recently, people start to debate on the observations of 3 and 0.5 keV light, which is associated with the dark matter decay, particularly sterile neutrino. Do you see or do you expect to see it in the spectra of the core collapse supernova, since 99% is emitted neutrinos?
So I haven't looked into that. There may be a sterile neutrino paper looking at that line and seeing what they can predict from that, but I don't remember seeing any paper on it. So I don't know. none of us put sterile neutrinos in our, we only put them in some of our calculations. We typically ignore sterile neutrinos in our calculations. So if you ask me, what do I actually believe in sterile neutrinos, not enough to put it in my code for the most part. So I would rather put it in magnetic fields first, so that although the sterile neutrinos might be easier. But that's where we're at. So there's not that many calculations. Alex Kosenko would know this answer right off, but I haven't seen any paper on it.
Another question, please. I was thinking about other implication of these sterile neutrinos because, as far as I understand, they are not a science standard model. And we have this difference in the Hubble constant, so the Supernovae has maybe 74, and Planck results give us 68. So, and if we include the sterile model to the standard model, sterile model, is it probable that Planck results, because they are quite model dependent, will change? I mean, it was a Hubble constant, so it should actually, I think it should increase Hubble constant.
Yeah, I'm trying to remember what, this was discussed at this workshop that I was at. Alex Kosenko argued very strongly that it makes the data fit better. So he argued, yes, it does, and it makes everything agree better. He's a proponent for sterile neutrinos, so he argued there were several things that it makes fit the cosmology better when he includes this. I would have to, I'll admit that beyond that, I don't know. I know that, so I remember there were several talks saying, yes, we need the sterile neutrino. It makes everything, it explains things like these features much better. But I can't remember exactly the results on that. To be brutally honest, it's not, sterile neutrinos are pushed by the particle physicists. So the particle physicists love sterile neutrinos. This is a big thing that they study. The supernova field, only every once in a while, when they coerce us, study sterile neutrinos. And Georg actually, in his talks, doesn't even use, so he's not a sterile neutrino fan, so he's one of the neutrino guys that is not. So my guest lecturer doesn't help me either.
Another question? It's your last chance.
Okay.
Well, obviously, you have all the information you need, so let's thanks again.